Okay. Okay, so the crux of our project is that we're exploring the influence of backgrounds on out of distribution behavior recognition. So often what you'll find is that when train and test videos are drawn from the same distribution, models perform pretty well. But as soon as you move into an out of distribution setting, model performance collapses, right? And we find that a lot of the information that's actually learned by these models and which allows them to perform well in an in-distribution setting is they can learn background features, right? So if you look at this, this is like an in-distribution setting. So you can see that all of this background information, the water, the rocks, means that actually there's very little reason for the model to actually have to be able to learn the behaviors themselves. It can just learn the correlations between the backgrounds and the context in the scene and the behaviors themselves, right? And so here's an example of what happens. We train two visual architectures, as you can see here. And as soon as you move into this out of distribution setting, you can see that the model collapses, right? But there are interesting differences between the architectures. So you can see in distribution that the ResNet and the transformer perform, comparably. But when you move to an out of distribution setting, now you get a big difference here. You go from a 2.5% difference to nearly 13% difference in performance. So what this suggests is that the transformer is better at disentangling foreground background information. And specifically, if you train these models on only the background information, you can get to what these red bars are, right? And this is significant considering that the background-only models don't ever see a chimpanzee during training time. They only see the backgrounds, so they perform really quite well. And when you look at background explicitly expressed as a proportion of foreground behavior, this is what you see, right? So 80%. So if you think about this background to foreground performance ratio as a proxy for background reliance, this is high, 80%. This is 4 out of 5 samples correctly classified by the foreground model are also going to be correctly classified by only using background information. And here you can see this really explicit difference between the two architectures when you move from an in-distribution to an out-of-distribution setting. With the ResNet, you see that the reliance is increasing, and with the transformer, you can see that it's actually decreasing quite significantly. So it's disentangling things quite well. But contrary to this kind of finding, we also perform these experiments where we actually concatenate background frames to the foreground videos. And the reason that we do this is because we have untrimmed video. So they're motion-triggered cameras. So what happens is you get a lot of activity in the beginning, and then you can get many frames which are contributing just background information. And so while the transformer is a little bit more resistant in its out-of-distribution setting, it actually becomes more sensitive than the ResNet to increases in background duration. So you kind of have this paradoxical situation where it's more resistant in the out-of-distribution setting, but at the same time more sensitive to increases in temporal background information. And then I guess to sort of round this off, we find that a kind of intuitive way to think about mitigating this is simply to subtract the background information from the foreground. But we find that if you do this in input space, so a pixel-wise subtraction of the foreground of the background, this doesn't lead to good performance. In fact, it harms performance compared to the baseline. But what you do get is, if you do this in latent space, where the intuition remains approximately the same, it's like a weighted subtraction of the background features from the foreground features in this latent space. And the key really is that now you can control the strength of the subtraction. So as training progresses, we decrease the strength of the subtraction so that you eliminate the shortcut learning early in training and then allow the usefulness of the background information to become apparent later in training. And you can see that you get good improvements, especially in an out-of-distribution setting. And this is kind of as simple an operation as it can get. There's nothing learnable here. It's literally an algebraic subtraction in latent space, and it works quite well. And the crux of the whole thing really is that we publish this big data set to allow for these things, where you have this in-distribution view, this out-of-distribution view, and for every foreground video, which we define as having a chimpanzee exhibiting any number of behaviors, we also have a background video taken from the exact same camera location. So you can actually do real-world experiments as opposed to previous works, which use these kind of synthetic mechanisms where they segment the animal, which takes a lot of manual annotation effort, and you do this mean pixel value filling to eliminate the animal. And what we show is that actually these synthetic background videos are quite a good proxy for real-world backgrounds, but there is a residual activity signal. So the studies which use this kind of thing are not entirely conclusive when they quantify their background impact, and that's what our data set allows you to do, as well as the other experimentation.